Welcome everyone to this week's Udacity Deep Reinforcement Learning Nanodegree weekly webinar. And happy Easter to everyone as well. It's Easter Sunday here. This week I'll be continuing on from what I did last week. I looked at convolutional networks. And this week I am going to be looking at policy gradient methods. Most of you have probably finished or finishing your current project for value-based, and you'll be moving on to policy gradient methods or policy-based methods. Some of the students are already onto this section, but I thought it would be a good thing just to go over the basics and an introduction to sort of give you guys a bit of a heads up before you get into the the third part of the course and get on to the policy-based methods. So basically what I'll be going through is policy gradients explained, an introduction. I'll be going over the objective, input features and rewards, optimization, intuition, policy gradient with Monte Carlo rollouts, policy gradient with automatic differentiation, policy gradient improvements, policy gradient improvement baseline, vanilla policy gradient algorithm, causality, and then reward discount. Then after that, we'll have a bit of a Q&A and go through bits and pieces of it. So, policy gradients explained. The policy gradient methods, PG, are frequently used algorithms in reinforcement learning. The principle is very simple. We observe and act. A human takes actions based on observations, as a quote from Stephen Curry. You have to rely on the fact that you put the work in to create muscle memory and then trust that it will kick in. The reason you practice and work on it so much is that so during the game, your instincts take over to the point where it feels weird if you don't do the right way. Constant practice is the key to build muscle memory for athletes. In policy gradient, we train the policy to act based on observations. The training in policy gradient makes actions with high rewards more likely, or vice versa. We keep what is working and throw away what is not. So think about that and move on to the next section. So here is, for example, Stephen Curry doing a basketball shot and all the different frames. So if he was the agent, there would be different points where he'd be moving his muscle joints and so on. So now, in policy gradients, let's say Curry is our agent. He observes the state of the environment. He takes the action based on his instinct, policy, on the state S. He moves and the opponent reacts. A new state is formed. He takes further actions based on observed state. After a trajectory of motions, he adjusts his instinct based on the total reward received based on that trajectory. Think about this, in real life and how this involves. Curry visualizes the situation, instantly knows what to do. Years of training perfects the instinct to maximize the reward. In RL, the instinct may be mathematically described as policy giving the action, or the action given the state. The probability of taking the action given the state, policy is the policy in RL or pi. For example, what is the chance of turning or stopping when you see a car? So if that was convolutional, so that's the action in the state. Given car, what would you do? So here's a formula. So how can we formulate our objective mathematically? Expected reward equals the sum of the probability of a trajectory x corresponding rewards. So it's the expected reward, the sum of the probability. Look at that. So then basically, and our objective is to find a policy that creates trajectory that is optimal. So basically, we then maximize the expected reward, as you can see, based on that trajectory, given the policy. So that's now we get on to input features and rewards. So S can be handcrafted features. So the state can be handcrafted features from the state, like joint angles, velocity, or a robotic arm. In some problem domains, RL is mature enough to handle raw images directly. Pi can be deterministic policy, which outputs the exact actions to be taken, move the joystick left or right. Can also be a stochastic policy, also which outputs the possibility of an action that it may take. So what we need to do is we need to record the reward given at each time step. In a basketball game, all are 0 except the terminate state, which equals 0, 1, 2, or 3. Let's introduce one more term H called horizon. We can run the course of simulation indefinitely until it reaches the terminate state, or we set a limit to H steps. Optimization. First, let's identify a common important trick in deep learning and RL. The partial derivative of a function is equal to the function times the partial derivative of the log function x. So basically we replace fx with a policy, then we have that. Also, for continuous space, expectation can be expressed as the following. That's the expected probability function. Now, let's formalize our optimization problem mathematically. We want to model a policy that creates trajectories that maximize the total rewards. However, to use gradient descent to optimize our problem, we need to take the derivative of the reward function, r, which may not be differentiable or formalized. Let's rewrite our objective function, j, as. We've changed that, and now we've turned it into that. The gradient, or policy gradient, becomes the following. I'm not going to read all that out, you guys can have a look through that now. Now, great news. Policy gradient can be represented as an expectation. It means we can use sampling to approximate it. Also, we sample the value of R but not differentiate it. It makes sense because the rewards do not directly depend on how we parameterize the model, but the trajectories are. So what is the partial derivative of the log pi given the trajectory? So the trajectory is defined as and then we take the log and then the first and the last term does not depend on the policy, so it can be removed. So we can take that out, we can take that out, and then we're just left with that plus that. So the policy gradient becomes and we use the policy gradient to update the policy, as you can see here. Now, intuition. How can we make sense of these equations? The underlying term is the maximum log likelihood. In deep learning, it measures the likelihood of observed data. In our context, it measures how likely the trajectory is under the current policy. By multiplying it with a reward, we want to increase the likelihood of the policy if the trajectory results in a higher positive reward. On the contrary, we want to decrease the likelihood of policy if it results in a high negative reward. In short, keep what is working and throw out what is not. If going up a hill below means high reward, we will change the model parameters policy to increase the likelihood of trajectories that move higher. There is one thing significant about the policy gradient. Probability of trajectory is defined as the following. So, states in a trajectory are strongly related. In deep learning, a long sequence of multiplication with factors that are strongly correlated can trigger vanishing or exploding gradients easily. However, policy gradient only sums up the gradient, breaks the curse of multiplying a long sequence of numbers. So the trick basically creates a maximum log likelihood, and a log breaks the curse of multiplying a long chain of policy. So here's policy gradient with Monte Carlo. So here's the reinforcement algorithm. Here is a reinforcement which uses Monte Carlo rollout to compute the rewards. Play out the whole episode to compute the total rewards, as you can see. So basically, the policy gradient can be computed easily with many deep learning software packages. For example, this is a partial code for TensorFlow. Yes, as often, coding looks simpler than explanations. So what you've got here is logits, using softmax. We've got the loss for reduced mean and the gradients. Quite basic. So, continuous control and Gaussian policies. So how can we model continuous control? Well, here we are. We sample the directory from the policy, given the state and action with the quotation, and basically rerun the policy. And let's assume that the values of the action are Gaussian distributed. From there. And the policy is defined using a Gaussian distribution, which means computed from a deep network with the following. We can compute the partial derivative of the log policy as log, you can see, equals to, like I said, I'm going to go through all of it. Read through it, and then we can back propagate. And here is the slight variance. So through the policy network, to update the policy, the algorithm will look exactly the same as before. Just start with a slightly different way in calculating the log of the policy. Policy gradient suffers from high variance and low convergence. Monte Carlo plays out the whole trajectory and records the exact rewards of the trajectory. However, the stochastic policy may take different actions in different episodes. One small turn can completely alter the result. So Monte Carlo has no bias, but high variance. Variance hurts deep learning optimization. The variance provides conflicting descent directions for the model to learn. One sample rewards may want to increase the log likelihood and another may want to decrease it. This hurts convergence. To reduce the variance caused by actions, we want to reduce the variance with the sample reward. So increasing the batch size in policy gradient reduces the variance. However, increasing the batch size significantly reduces sample efficiency. So we cannot increase it too far. We need additional mechanisms to reduce the variance. So here is the baseline. We can always subtract a term to the optimization problem as long as the term is not related to policy. So instead of using the total reward, we subtract it with the value state. We define the advantage function A and rewrite the policy gradient in term of A. So, in deep learning, we want to input features to be zero-centered. Intuitively, I was interested in knowing whether an action is performed better than the average. The rewards are always positive. Policy gradient always tries to increase the trajectory probability even if it receives much smaller rewards than others. Consider two different situations. So in situation 1, trajectory A receives plus 10 rewards and trajectory B receives minus 10 rewards. Situation 2, trajectory A receives plus 10 rewards and trajectory B receives plus 1 reward. In the first situation, PG will increase the probability of trajectory A while decreasing B. In the second situation, it increases both. As a human, we would likely decrease the likelihood of trajectory B in both situations. By introducing a baseline like value, we can recalibrate the rewards relative to the average action. So here is a generic algorithm for the policy gradient algorithm using the baseline B. So basically we initialize the policy parameters and baseline B for iterate over a certain amount. We collect a set of trajectories by executing the current policy. At each time step in each trajectory, compute the return and the advantage estimate. We refit the baseline by minimizing the baseline in the state minus the reward, summed over all trajectories and time steps. We then update the policy using the policy gradient estimate, which is the sum of the terms. And then from that point, we look at this. So the causality. Future actions should not change past decisions. Present actions only impact the future. Therefore, we can change our objective function to reflect this. So we've changed that. And now we basically have the reward discount reduces the variance, which reduces the impact of distant actions. Here, a different formula is used to compute the total reward. And then corresponding objective function becomes this. So that was probably one of the more shorter webinars that I've done. It's probably got quite a fair bit to think about, and it is a little bit complex. I only wanted to get just the basics out for today and to build upon what you're learning in the course material. Or hopefully this explains the course material in a slightly different way. What I'll actually be going through maybe next week, algorithms themselves in PyTorch, especially reinforce, and go through, probably proximal policy optimization and active predictive methods in more detail. This is more to add on to what you've been existing doing. So I hope it helps a little bit. And if you've got any questions, send them through now in YouTube or ask them later on Slack. So, like I said, this is probably a little bit of a shorter webinar than usual, but I thought that it was probably a fair bit to go through as I was getting through most of the maths, and it's going to add on to what you're already doing. So, got any questions? I'll wait for them now. All right, well, thank you very much, everyone, for this webinar. I'm going to be on Slack for the next probably 40 minutes. So if anyone's got any questions, just direct message me and I'll respond to any of the parts from this right now. Thank you very much, and I will talk to you guys next week. Like I said, going a little bit more into the code itself. Thank you.